Thank you, Cecilia. Thank you all for being here until the end. And so I'm going to tell you a little bit about what we're doing just 120 miles south from here at UC San Diego. And there is not going to be much machine learning, but I try to combine what machine learning and physics-based models can allow us to do nowadays. And the work that I'm going to present started a few years ago with Greg Madders and Volodymyr Babin, and then it's been carried out by many other people, and it's been funded by many different sources, but today I will primarily talk about work that has been funded by NSF and the Department of Energy. And we have been very fortunate to have many different collaborations with experimentalists and theorists. Okay, so now, if you read any papers about water, the introduction probably starts with something like this. The importance of water cannot be overemphasized, and there are many different examples from hydration of biomolecules, heterogeneous chemistry, water-aid interfaces for desalination, and things like that. And of course, we are very happy to make these beautiful pictures, but then the question is always like, are these pictures meaningful in the sense that is a good representation of the reality or are just fiction? And water is a good example. If you go to this website, you will find out that there are hundreds of different models. These are the ones that have been listed on this website. And because of that, obviously, you will also understand and learn very quickly that not only water is important, but also surviving in the water communities can be very harsh because of these different models, and everybody believes that their model is the one that actually works. And so over the years, we learn not only about water, but also how to survive in water. And this is a surfer competition in Australia a few years ago. Okay, so now what I'm going to try to tell today is about I'll try to address two questions that I think also were raised this morning. The first one was about, we have obviously working with models, and so there is a question about how good are the data that are used to build the model. And the second question is, how good is the model in representing the data that we have? And these two questions are obviously separated, but intrinsically they are entangled, because if you want to make predictions, you really need to have good data and also a way to represent this data in an accurate way. Okay, and so this brings me to an important issue in molecular simulation. There is what that is called validation and verification. There is this nice report from the National Academies of Sciences that emphasizes the importance of computational sciences nowadays, but also the importance of addressing the issues of uncertainties that are associated with these simulations. Of course, anytime that we perform a simulation, there is an error associated with that. And addressing it, assessing these errors is going to be important in order to understand what is the validity of our predictions. And so if you think about, molecular simulations, essentially what we are trying to do is to sample a distribution from some partition function, depending on the ensemble that you are working on. And of course, if you are in the classical regime, you are going to use an expression for the partition function that is like this. But we know close to our heart that nature is not really classical. Classical is a limit of what is a quantum world. And so in reality, we should use a quantum partition function. And of course, once we have this ingredient, then we come up with our molecular properties, with our molecular mechanism, we make predictions, we try to understand experiments. And everything works beautifully. The important point here is that everything that we say here depends on how good we are at describing this Hamiltonian here. And so this molecular Hamiltonian essentially is the key ingredient in order to make a computer simulation that is predictive. Okay, so now if we go back to our water molecules, if you look at your glass of water, we are very familiar with a picture like this. We have water molecules connected with each other with two hydrogen bonds, and obviously this hydrogen bond network is fluctuating in time and in space. And so we are very familiar, probably many of you, with force fields. I just put this up for people that are not in the computational sciences world. So the force field has been very useful to start the world of computational chemistry and physics, essentially. And so what we are trying to do is to model the motion of atoms in a molecule using simple expression, like harmonic springs for bonds and angles. Water doesn't have any torsion, so we can ignore that part, and we have then intermolecular interaction based on some electrostatic mapping and some non-bonded interactions. Obviously, these potential energy functions are very simple, are very fast, but also lack any predictability. Nothing is harmonic in the world, right? Okay, but we know what is the solution. We need to solve the Schrödinger equation, and there are many different flavors. Yesterday, Kiron talked about the Kohn-Sham equation. Anatol mentioned many different times of many different approaches to electronic structure. And so what we can do nowadays is probably very popular density functional theory from Kohn and Sham, and there are many different post-Hartree-Fock methods, which is the simplest way to solve the Schrödinger equation. And then if you put everything on a map like this by Martin and Gordon, I go here, it's easier. It's what you can see is that if this is the exact treatment, so if this is how nature works, the best approximation that we have to calculate these potential energy functions is this couple cluster with single, double, and iterative triple excitations. Very long acronym, and also very expensive. You can see that Martin was suggesting that by now we should be able to do maybe a few tenths of atoms just to calculate the energy. Essentially, you cannot calculate forces at the couple cluster level because there are non-analytical forces, so you need to do by finite difference. So if you need to do many of these calculations, it's essentially impossible. And that is the reason why you go up, and so you go far from the exact treatment, and you ended up in methods like many-body perturbation theory, quantum Monte Carlo, density functional theory. And now you can see density functional theory. Probably Martin was a good predictor. You can do thousands of atoms nowadays, but of course now the difference with exact treatment becomes larger and larger. So you're now in a realm where you can actually perform simulations, but the predictive ability of this simulation is somewhat questionable. And so the question is, okay, we have force fields that are, no, I need to go here, I think. Not accurate but cheap, and ab initio that can be accurate but expensive. And so the question is how we can go beyond this. And yesterday, Anatol mentioned many different approaches to solve this problem using neural networks and machine learning, starting a long time ago. And probably I missed some of the players here. It's not on purpose. But essentially what we do is that you build training sets for molecules, and then you let the machine learn how the interaction changes depending on the local environment that you are around these atoms. And of course, this network can be expanded to the condensed phase, for example, for your glass of water. And Winanin, starting from Beryl Parinello and Winanin a few days ago, showed that you can have a neural network that map some ab initio trajectory from density functional theory, and then the neural network allows you to perform simulation faster and for larger systems, but still with the DFT accuracy. And I showed you before that the DFT accuracy may not be great for different systems. And so I'm going to try to give you a different perspective, and it's a perspective based on many-body interactions. And so if you look at this water hydrogen bond network, this looks like a graph. And a few days ago, there was the talk by Peter about these graph networks that is somewhat related to how a hydrogen bond network may look like. But what I'm trying to do is to say, okay, now this glass of water is moving, all the molecules feel each other, and they change position, they change their distortion over time. But this energy for this glass of water comes from the contribution of many different molecules. And so what I'm trying to do is to say, well, if I have my glass of water, maybe I can reconstruct the energy of this glass of water by looking at the contribution of individual molecules first. And then, of course, these individual molecules are not in the gas phase. They are in an environment, and so they are perturbed by the molecules around them. And so I can look at these two-body effects, so the perturbation that comes from the fact that these two molecules are interacting with each other, and so they are not isolated one body anymore. And of course, in this glass of water, I have many different two-body types of interactions, depending on the distortion of the molecules and depending on the distance and the orientation. And then, of course, I have three-body interactions. So I'm going to look at what is the effect of adding another water molecule to a dimer that I already have. And again, I have many of these. And I keep going this way to the 4-body, to the 5-body, 6-body, up to the n-body. And so now what I'm trying to say is that, well, I can reconstruct the potential energy surface of a many-body problem on a many-body system by using this many-body expansion, where I can reconstruct the energy of this n-body system by adding individual contribution coming from one body, and so the energy of the one body in the n-body configuration, the two-body, which is now the energy of the dimer minus the energy of the one body, three-body, that now are the energies of all possible trimers minus all possible dimers minus all possible monomers, and keep going this way. And so now what I've done is just recast the problem in a different problem. The complexity is still the same because I still need, if I need still the n-body contribution, I'm still limited by the accuracy of couple cluster and the ability of doing couple cluster calculation, which is limited up to tens of atoms. However, and this has been shown a long time ago, the many-body expansion converges quite quickly for any system that is non-metallic. So for weakly correlated systems, for systems where the energy gap between the valence and conduction band, essentially, between HOMO and LUMO is large, then this series converges quite quickly. That doesn't mean that you can ignore many-body effects, because in the condensed phase you have many body effects, but maybe this suggests that the nature of the interaction changes depending on whether you are in the low-order regime of many-body interactions and the high-order regime of the many-body interactions. And I will try to explain this better. Now we go back to this net picture, but now we put back the electron densities. And now what you can see, this is a picture, but it's quite close to what you will see if you actually do an electronic structure calculation for a glass of water. What you can see is that now this hydrogen bond network connects water molecules that share electrons in only localized regions. This molecule here doesn't share any electron with this molecule up here. And so now, in this region where the molecules are sharing electrons, we need quantum mechanics, because these are the regions where you cannot assign electrons to one molecule or to another. They are completely shared. And since they are fermionic particles, they need to obey the properties of quantum mechanics for a fermionic system. And so these are the regions where exchange, charge transfer are important. But of course, the exchange between electrons of this molecule and electrons of this molecule can be completely ignored. This doesn't mean, and charge transfer as well, this doesn't mean that this molecule is not interacting with this molecule up here, because all these molecules are polar and have polarized abilities. And so this implies that if I change the electric field somewhere in my system, the entire system responds. And so I change the electric field here, and this molecule up here, we respond because everything is changing. And so there is still an interaction, but now this interaction between this molecule here and the molecule up here is purely classical. It's described entirely by the multiple description of the electron density of an isolated water molecule. And so now the problem becomes interesting, because if I go back to my many-body expansion, what I just showed you is that, of course, I need all many-body effects, but there is a distinction between the nature of these interactions. At the low order, I need quantum mechanics, but at the high order, this can be described just by classical mechanics. And of course, the region of overlap is a little bit blurred because it depends on the molecular system that you're looking at. But now the things becomes interesting, because if I imagine that I only need to do one body, two body, and three body interactions at the quantum mechanical level for water, the three body interactions involve 9 atoms. Those are well below the limit of couple cluster calculations. And so I'm actually up here, down here. And this can be done even in the 2000. And so now I transform a problem that was many-body and is still many-body, but I separated the nature of the interactions in two different regimes, a regime that requires quantum mechanics and the regime that can be described correctly at the classical level. And so what I'm trying to do in the next few minutes is say that, okay, now I can learn this low-order many-body interaction from data, and instead I learn the higher-body interaction from physics, because I definitely know how to use electrodynamics and electrostatic interaction to describe these higher-order interactions. And so now the problem becomes much more simplified than what Winanin was trying to address a few days ago. Because now what I need to learn is just the difference between my n-body interactions and my classical mechanical description of these n-body interactions, and not for all the many-body interactions, but only for a limited number of these many-body interactions that are the low-order interactions. And so what I'm going to do is to try to learn this difference between the classical description and the fully quantum mechanical representation of these many-body interactions, but one contribution at a time. So I was able to disentangle this interaction, then I will glue everything together to get my potential energy surface. And so just to give an example on the two-body interaction of a water molecule, essentially what I'm trying to do is to describe an interaction that looks like this, where R is the separation between these two water molecules. And so here I have a classical contribution that depends on the electrostatic interactions between the densities, an induction contribution coming from the fact that one molecule polarizes the other molecule, and a dispersion contribution. So all these three terms can be calculated quite easily just looking at the property of an isolated water molecule. And so these are easily accessible by knowing the physics of the problem. And of course, this combination of these three terms are exact in the limit where these two electron densities are not overlapping. So I can calculate the energies at these distances without doing a couple cluster calculation for the entire dimer, because these two molecules are so far apart, they do not share any electrons. And of course, this classical representation also provides an approximation here. But now here things become complicated because the electron densities overlap. And now I cannot distinguish which electron is which. And so here, I need to do quantum mechanical calculations. Here is where I need couple cluster. But now what I need to do is to generate huge training sets of possible two-body interaction that I can map into any machine learning approach that you like, and glue everything together to get a potential energy curve for the two-body interaction that is exactly at the couple cluster level, at any distance and for any different orientation. What is interesting is that, and I would like to mention this, that at short range, this interaction essentially involve the interaction between field and field orbitals, and field and empty orbitals. This is the Pauli repulsion, and this is the charge transfer. And these are exactly the components density functional does very poorly, because the energy gap predicted by density functional theory is always very poor. And so here is actually the region where, in my opinion, density functional is suffering the most. So now how can we map these two-body interactions? We started our original work by using standard ridge regression, by using as our interpolant permutation invariant polynomials. These permutation invariant polynomials are functions that are well known in applied math, and essentially trying to reconstruct a potential energy function in our case, but in a multidimensional potential energy function, in terms of monomials, where these monomials are exponential function of the distances between all possible physical atoms in our molecule. And we have first-order polynomials, second-order polynomial, third-order polynomials. And what we need to do is to find these coefficients A. And so now, why are interesting in our field? They are interesting because they impose the permutational invariance directly just by construction. We know that the energy of a molecule doesn't change if I exchange these two atoms or if I exchange the two molecules at all. And so this is because of the property of the Hamiltonian. And so the permutation invariant polynomials essentially allows me to build a mathematical function that is compact enough and guarantees both the translational, rotational, and permutational invariance of my functions. And so then what we do is just to use a ridge regression to get our coefficients A, and we use a regularization, and so these standard things for all of you. Okay, and the same thing can be done at the three-body level. Because again, we have this part here that comes directly from physics. You don't need to do any calculation for the entire system. You just need a good calculation for an isolated molecule to get these properties here. And of course, now when these molecules are interacting with each other and they share electrons, there is the need of quantum mechanical information that we do using these permutation invariant polynomials as well. Okay, does it work? It works quite nicely. These are thousands of couple cluster calculations for 2-body and 3-body energies. And you can see that the model on the y-axis is able to reproduce the couple cluster results on the x-axis essentially with the same accuracy. And these are couple cluster calculations in the complete basis set limit, because now we have like 6 atoms and 9 atoms. These are trivial jobs. And all these calculations are independent of each other. So if I have the possibility to run all 40,000 calculations on at the same time, this calculation will take at most 30 minutes. The interesting thing, that is what I think this approach may be useful to interpret what is going on in the condensed phase, is that all higher body terms, as you can see here, can be described very nicely by classical representation. So our 4-body here comes from the polarizability of the molecules, and so these 4 bodies are just the classical 4 bodies that come from induction. And you can see, and those are not being trained, these properties just come from the polarizability of the molecules and how you map this polarizability into an efficient representation of the molecule. And so this allows us to show that you can have an n-body energy that is couple cluster at any order, but just by doing couple cluster calculation for 2-body and 3-body energies, and a couple cluster calculation for the 1-body monomer. Now just go back one slide. So I show you that we use permutation invariant polynomials. We actually love permutation invariant polynomials because they build the symmetry already intrinsically by definition. But of course, they are not so fancy as neural networks. So we say, well, let's do neural networks as well. And so we joined forces with Michele Ceriotti, Gabor Shani, and Jörg Beller. And we used the same training set that we used to build the MB pole at the beginning using permutation invariant polynomials. And now you use the Beller-Parinello neural network, so standard things for most of you. But then you say, well, Gabor was feel alone, and say, well, we can use also GAP. And so we use the Gaussian approximation potentials, the same training set. Now what Gabor Shani does, he needs a descriptor for the local environment. We use is a SOAP approach. And now what you need to do is to optimize these B coefficients. And again, you can use a standard ridge regression. And what we find out, obviously, with no surprise, that if you look at the training set error and the test set for 2-body and 3-body energies, you see that all 3 methods essentially give you the same accuracy. If you want to be picky, you will say that the permutation invariant polynomials are probably the most stable, because you can see there is not much difference between training and test errors. The gap potentials are probably the most prone to overfitting, so you need probably much more data to train a gap potential, and the neural network in the Beller-Parinello framework are probably in between. But that, in my opinion, is an important point of view, is an important results from a physics point of view, because essentially this is telling us that if you have a good representation, a physical representation of the energy landscape, it really doesn't matter how you describe these many-body contributions, as long as the mathematical function is flexible enough to capture all these possible distortions. Now that we have a potential energy surface, we can do molecular dynamics simulation that are much faster, obviously, than couple cluster. You cannot really do couple cluster, but even much faster than density functional. And since they are so fast, we can even afford not just to do classical MD, but to do quantum MD, where we actually quantize also the nuclei. And you know that now the hydrogens are fuzzy because the 0-point energy effects, and you may have tunneling, and so are things that are not described by classical MD. And so depending on the size of the system, we can do molecular simulations using basis set expansion for small clusters. We use path intramolecular dynamics and centroid molecular dynamics in the condensed phase. And if you are interested in tunneling properties, we can use ring polymer instanton. So I want to just mention 2 things. So these methods here, basis set expansion and path intramolecular dynamics, are numerically exact in the sense that if you have a potential energy function and if you are able to converge your calculations, they will give you the exact quantum properties for the system in hand. Centroid molecular dynamics and ring polymer instanton instead are approximate theory, and so even if you have the exact Hamiltonian, the result that you are going to get with these two methods are not going to be the exact quantum mechanical results. And so just very briefly, I will show you that these things work, and I will try to use this method to learn something about the physics of the system. So this is a vibration rotation tunneling spectrum of the water dimer, which means that we are looking just at two water molecules bound together, and we are looking at all possible vibrations. As you can see, these experiments are in wave numbers. Wave numbers is a very small amount of energy, and you can see that our calculations are essentially the same accuracy as the experiment. We can go to a larger cluster. This hexamer, and we will go back to the hexamer later. These are vibration. These are the infrared spectrum measured by Mark Johnson at Yale. These are experiments that are measured by Rich Sekali at Berkeley, and these are our calculations. And again, you can see there is almost a one-to-one match between the experiment and theory. We can go to the liquid water, and now here are the RDF, the oxygen-oxygen RDF that probably Winan showed a few days ago. I already told to Winan, so I showed these things to Winan, so Winan knows about this. And you can see that now MB-Pol is able to reproduce the experiment without knowing anything about how liquid water looks like. Our model only knows about one body, two body, and three body. Everything else comes because the physics of liquid water works very nicely in this many-body expansion. And so our model doesn't know anything about liquid water and is able to reproduce the RDF very nicely. Not only this, if you look at the infrared spectrum and the Raman spectrum, you can see that our calculation match almost one-to-one the experimental results. Even if you go down here where there is zero absorbance and you zoom in here, you can see that even those features are reproduced. And so this is quite an accomplishment, in my opinion, because there was no other model that was able to go from the dimer to the liquid water with such an accuracy. Not only this, this is important actually. And so more recently, just by coincidence, we also look at the isothermal compressibility of liquid water in the supercool regime. And these are our calculations. There were no experiments down here, and now the experiments that have been done actually match quite nicely MB-Pol. These are simple force fields, T4P, and this is a polarizable force field. And you can see that all of them actually fail after you go down in the supercool regime. And so this again is showing that MB-Pol not only is transferable across phases, but also within the same phases is able to reproduce metastable states of liquid water, because the supercool regime is a metastable state. We went to ice, and we were able to look at the energetics of the different ice phases. I just show you here the infrared spectrum of liquid water, of ice 1H, and this is the experiment. These are the calculations at the quantum mechanical level, and you can see there is a pretty good agreement. And I would like to mention that the quantum dynamical calculation here are now approximate because we use centroid molecular dynamics. We went to the SFG, and we actually showed that previous experiment that showed this positive feature here were not done correctly, and in fact they changed it later on, the same experimental group, and showed that there is no positive feature here. And this was never in our simulations, because this positive feature here cannot just exist by physics. The shape, the sign of this spectrum indicates how water points at the interface. Positive feature means that the waves are pointing up. Negative feature means they are pointing down. So a positive feature here at low frequency means that you have ice-like structure, because it's very red-shifted, so strongly hydrogen bonded, but you are very close to the interface because you are pointing it up. So that obviously was an artifact of the experiment, and you can see that our calculations in red have the same accuracy of the experimental measurements made by the same group in two different years. Yes?
So in the left plot, classical versus quantum means Born-Oppenheimer versus predictive?
Yes. This is Newton dynamics versus centroid molecular dynamics.
So the quantum.
The quantum nuclei.
Is very important.
Yes. Yes. If you go down in temperature, nuclear quantum effects becomes more and more important. Then we say, well, we don't have any electrons here because we mapped this into this many-body expansion. And so we joined forces with Julia Galli at U Chicago, and we use our configurations to look at the energy gap between the valence and the conduction band of water in the bulk using classical nuclei, so classical Newton dynamics, so path intramolecular dynamics, and then the difference between the energy gap at the surface of liquid water and in the bulk. And you can see again, this is actually quite important and relevant for people that are interested in the electronic structure, because you can see that even small differences in the hydrogen bond network between quantum nuclei and classical nuclei make a big difference in the energy gap in the bulk. And there is an energy gap difference between bulk and surface. So these are relevant because if you look at electron affinity, or if you look at the hydrated electron, experimentally it's very hard to know where the electron goes. And definitely the energy gap is different depending on whether the electron is in the bulk or is at the interface. Then we join forces with Shifan Wu at Temple, and we calculate the X-ray spectrum of liquid water. In gray is one experiment. In red are our path integral simulations. In blue are the classical nuclei simulations. And you can see again that the agreement between our simulations and the experiment are quite remarkable. And again, there is a difference between classical nuclei and quantum nuclei, and this is liquid water at 300 Kelvin. Of course, this X-ray is a local probe. And so, of course, quantum effects in the hydrogen bond dynamics are very important in this short-range regime. And we can explain this by the delocalization of the molecular orbitals that are now allowed in the quantum world that are not allowed in the classical world. So obviously this works very nicely in our hands, so we are happy. But then we were writing this Chem review article, and one of the reviewers said, well, you need to rank the models that you are talking about in this review article about advanced water models. And fortunately, Angelos Michelides, Dario Alfé, and Mike Gillan had just came up with this review on density functional theory for water, and they had identified different properties for the monomer, dimer, and hexamer, and dyes that according to them are critical in order to reproduce the properties of water across the phase diagram. This is what they calculated, and they ranked their density functional models. We use the same properties, and MB-Pol looks like this. And again, these are properties that 3 people completely independent of us chose, and MB-Pol didn't know anything about this property and definitely works very nicely. It doesn't work perfectly, and we are very happy because it's still a model, and so it shouldn't work perfectly. And obviously, we are even more happy when other people say that MB-Pol is actually working nicely and is perhaps one of the all-around best molecular models for water that has ever been derived. Okay, so now this works, but the workshop is about learning physics and interpretable models. So we think that this model is very interpretable because we have essentially the way to decompose the many-body interactions in individual contributions. So now we can plug and play and see what are the contributions that make up our condensed phase world. And so these are 3 questions that I will try to address if I have time. So the first one, what makes water water? So these are water hexamers. And for people that are interested in the water community, the water hexamer is a milestone for any water development because it's the first cluster that has this 3-dimensional hydrogen bond network similar to what you find in liquid water and in ice. These are the couple cluster results, and these are our MB-Pol results. Now, this is close, but what is even more interesting for us is that if I look at the individual contributions to this many-body energy and I compare the errors relative to the couple cluster, I can see that the model is actually able to reproduce every individual term with an accuracy that is very close to couple cluster. So it's not working because of error cancellation, it's working because it's capturing the physics right. So now we can play and say, okay, what happens if I use density functional theory? Yes?
Can you go back? I don't think I understand the plot. How do you know from the CCS? I mean, the CCSD, you cannot get the end body decomposition, right?
Yeah. Yes, I can, because what I can do, I take the cluster, and then I look at all the dimers, all the trimers, and I write the energies as a composition like this. So there are many couple cluster calculations. Okay, so then I can use density functional theory and these are density functional theory without dispersion. This goes from GGA, the simplest version of DFT hybrid. And you can see here is the B-leap that Andrew was showing a few days ago that he had to improve. And clearly he had to improve because obviously this model doesn't even capture the right order of the isomers, not even the energy. And then if you keep going, and you go a meta GGA, a hybrid meta GGA, and then hybrid meta, and range separated functional, you can see that none of these density functional models are able to reproduce the energies correctly. These two, the orange and the pink, at least get the right order of the isomers. This implies that probably the phase diagram is going to be shifted a lot in temperature and pressure because the interaction strength is predicted in a different way. Now if you add dispersion, everything looks magically better. And so now we are happy because if you look just at the total, if you make an observation of the total interaction energy, you see that the order is now correct. You have an error of a few kcal per mole. Yesterday was mentioned that by Kiron that 1 kcal per mole is what is defined chemical accuracy because at room temperature you have fluctuations of the order of 0.6 kcal per mole. So obviously they don't have chemical accuracy, but at least they capture now the right phase, the order of the energies. But now we can play a game with this many-body decomposition because we want to understand what is the underlying physics. And so this was what MB Paul was able to reproduce for this water hexamer. And now if I play with the density function, I get something like this. And so here is where the model becomes interpretable, because now I can definitely see that even if the total interaction energy look okay, it looks okay for the wrong reasons because there are error compensation at any order here. And so this implies that if I break this error compensation, the model becomes unreliable because the total interaction energy will also be different because I break the cancellation of error. For people that are interested in the electronic structure, this is quite, in my opinion, worrisome, because I showed you before that a classical model is able to reproduce the 4-body, 5-body, and 6-body energies quite correctly, because that is what MB Paul uses. These density functionals here have errors up to almost 2 kcal per mole at the 4-body level. This functional here has error at the 5-body level of 1 kcal per mole. This is an indication that it's not that the interaction energies are wrong, but the description of the monomer density is wrong, because obviously in the classical picture I show you that these energies come from the polarization of my monomer. And this is strictly related to what John Perdue said a few years ago in Science, say that modern functionals are diverging from what they should do because they're not able to reproduce the electron densities correctly. And you can see, in fact, that as you go up, if you go on with the years, then you get a lower total energy error that I showed you before, but a huge error in the density. And this is the reason why the 4-body, 5-body, 6-body are not correctly described, because you have an error in the electronic density. And so when you try to learn an electron density from DFT, maybe we are learning some errors and not really the physics of the system. Okay, so now we played and say, well, we can argue that these errors are small. And so we want to understand whether these small errors that we find at in this many-body decomposition actually affect the properties of water. And so what we did recently was to take 4 different functionals representative of what John Perdue defined the Jacob's ladder of DFT approximation, going from GGA, meta GGA, hybrid, and meta-hybrid range-separated functionals. These are the 2-body energies, coupled cluster on the x-axis, and the DFT model on the y-axis, 3-body energies in the same way. And you can see from a distance that actually things looks pretty good. You will say that, of course, there are some errors, there is some spread, but at least the 2-body are following the coupled cluster. The 3-body also, maybe these functionals, maybe the 3-body is a little bit worse because the slope is not really exactly as in the coupled cluster. And just as a reference here is MB Paul. And so what we say is, well, let's see what happens if I look again at this water hexamer. And so these are the water hexamers, the energies, coupled cluster, and DFT model. You can see that FPBD3, which has been proposed as a good model for water, actually it's not that good because it has huge errors at any order of the interaction. It improves when you go to the meta GGA. This scan is the function that Winan was showing. And you can see that the errors are quite remarkable in the energetics, but also in the many-body decomposition. And so now when you build a network on a functional like this, we are not learning much physics, because the physics is actually wrong already at the two-body level. And then we go to the RepPB0 and hybrid, and and the best functional that I think exists nowadays for a weakly interacting system in this omega B7MV. And you can see that now it's almost perfect, except at the three-body level, but it's very small. So then we say, okay, this MB-pole. We say, okay, this is how MB-pole works. We have this one-body couple cluster. In blue, we have this classical representation of many-body interactions. And we learn the correction at the two-body and three-body level. We can play the same game, and now instead of targeting the two-body and three-body at the DFT level, we can target, at the couple cluster level, we can target the DFT functions. And so what happens is that now, without using a neural network built on the entire water system, I can actually reproduce liquid water just using this many-body expansion. So what I've done here in gray are calculations performed by Tom Markland on a full box of liquid water with the path integral approximation. And the solid line is what we predict using the same functional, but now expressed in this many-body expansion. And you can see that we can do larger molecules, larger systems, and definitely faster. And we reproduce those values without actually learning the entire network of liquid water in the glass, in the bulk. So this is remarkable because, again, the low-order interactions essentially dictate how water looks like in the condensed phase, as long as you have a good description of the environment. And I want to point out, the agreement with RepPB3 is a little bit less good. And it's that because, as I mentioned, in our model, we only target the two-body and three-body at the FT level. All higher body interactions are still described by the MB-pole. And now you can see that RepPB3 has a huge error at the four-body level that is not compensated in our simulation. This is the reason why RepPB3 doesn't work very well in the many-body expansion. But then we can do something more. We can learn really how this many-body interaction looks like in the condensed phase, because now on a computer we can plug and play. And so we can say, well, we can build a Frankenstein model where I keep the two-body at the DFT level and the three-body at the couple cluster. If DFT is a faithful representation of couple cluster, I should be able to mix and match and get exactly the same answer. I can do the opposite, and I can keep the couple cluster at two-body and use the three-body DFT. We use this, we build these models, and then we perform the simulation of liquid water, 256 water molecule at the experimental density, and then it looks quite good. In gray is the experiment, in blue is MB-pole, and the other functionals are here. But now I relax the system, and I let the system find its own density. So I perform a simulation in the isobaric isothermal ensemble, and now you can see that there is a spread. All these four functions that were overlapping when I forced the experimental density, now they are providing different estimates, different predictions. Interesting. The PB family predicts more ice-like structures. You see it's more defined. The B97 functionals predict a more classical liquid, very dense. Then we go to the other systems. Okay, now let's see what happens if I use 2B DFT and three-body couple cluster. And now what happens is that omega B7MV essentially remain unchanged. So this implies that omega B7MV provides a couple cluster accuracy at the two-body level. All other functionals are failing miserably because the two-body were actually not good. If you go to the three-body, unfortunately, now things become worse also for omega B7MV because, as we showed before, there is an error at the three-body level, and this error at the three-body level actually shows up in the condensed phase very nicely. You see that it's getting this high-density liquid. If I put everything together, now I can explain what people see in the ab initio simulation of liquid water at constant density by just saying that what they are seeing is a compensation between two-body and three-body error. If I put these things together, I get this. As soon as I leave the system find its own density, actually these things don't work anymore because the compensation is not perfect. Why is this important? This is important because it's the first time, I think, that we can actually relate two-body interaction to the high-dense phase of liquid water and the three-body interaction to the low-dense phase of liquid water. And if you are interested in this, in the super-Q regime, there is an hypothesis, there is this competition between high-dense phase and low-dense phase that may give rise to a second critical point in liquid water. So now this analysis shows that if this second critical point exists, the potential energy surface that we need to use may need an accuracy that is probably not achievable even with MBPOL. And here is what SCAN looks like. This Winan he was mapping his network on a simulation with SCAN. And you can see that SCAN, because has this error at the two-body level, if you remember in my picture, the two-body level was over-binding, makes water a little bit too dense, too close, but also more ice-like. And when you relieve the density, so this is now in the MPT simulation, you are starting getting this high dense phase. What is interesting though, is that SCAN was described using constraints on the electron density. And now in fact, SCAN is able to reproduce three bodies, which are more classical-like correctly, because the electron density of the monomer is described correctly. It fails at the two-body level because it's a GGA functional, doesn't have any description of a correct exchange, and so obviously the function is limited. Okay, so what we can say is that now this many-body representation that can be learned just from a low-order interaction allows us to have a model that is transferable for liquid water across all phases, but also to interpret how liquid water looks like in different phases. So now we can use the same approach and say, what happens if I put a solute inside liquid water? Now we know that everything is going to be rearranged. The hydrogen bond changes, so we can put ions here. And of course, the model will work as well, because now I need to train even a lower dimensional space, because the ion here is just halides and alkali metals. Very easily, I can take many dimers, and I can learn the potential energy surface for my dimer, and put together two-body, three-body, and this classical representation, and I'm able to get a model that is always within, well below the 1 kcal per mole chemical accuracy, but much better than any other function. This for F minus, this Cl minus, this Br minus, and this is I minus. I can do the same for the alkali metals. These are errors with different functionals, but again, our models, our many-body models, have error close to couple cluster. And so now again, I have a function that works very nicely, is effective, is efficient, and now I can try to learn something. And so what we did is say, well, let's try to see what happens if I put an ion in solution, and I use simple point charge models, the same force fields that people use in classical molecular dynamics simulations. I took cesium plus, we have all the other ions, but in this presentation I show cesium plus, because cesium plus water and water-water interactions are very close. So small differences in how you represent the cesium plus water interactions are going to perturb the entire hydration shell. So a force field, as I mentioned before, is a pairwise additive, so it's not able to reproduce correctly the two-body because it's not meant to do that. It doesn't have any three-body. Then I can use a polarizable force field that Pratyush mentioned this morning, they're a better representation of the physics, and you can see that they're able to reproduce the two-body better and also the three-body better, but there is still an error. But the errors are relatively small, okay? And then I can go to our data-driven model and say, okay, let's see what happens if I correct for the two-body. And now I have perfect agreement with the couple cluster. I don't correct for the three-body, and so this is still the classical representation. And I can go and also correct for the three-body. Now I have a perfect couple cluster accuracy of the three-body. And now the question is, okay, are these differences meaningful? In the sense, I'm learning something new about the hydration of these ions. And I think that we can. So I put cesium in liquid water. I perform path-integral molecular dynamics simulations. And now these are the RDFs of oxygen and cesium plus. In red is the force field. And you can see it's very structured. So stronger, it overemphasizes the binding. I add polarization, and this second shell disappears completely. I collapse the second shell, and now I have a second shell much further, at 6.5 angstrom. I put back the two-body correction, and now I recover a well-defined second shell, but very different from what I got in the classical force field. I add three-body, I make this second shell even more pronounced. And I do path-integral molecular dynamics simulations, and there are small differences here and here. Okay, there are differences. Is this meaningful? Are we learning something? Well, we can look at the hydration shell. Here is what I plot our best simulations, but intra with correction at the 2-body and 3-body level. And on the right are the different models. You can see definitely there is visually a difference in the hydration shell. I put polarization, and now I destroy the second shell, as I mentioned before. Now it's much more expanded. I put back the 2-body, I get closer, and I put the 3-body classically, I'm very close. Okay, is this correct or not? We need to have a comparison with something that we trust. And so we joined forces with John Fulton and Greg Schenter at PNNL. They do X-ray XF spectroscopy. And so what we did was try to measure the XF spectra, calculate the XF spectra using the different models. So here is what we call an incremental RDF. So essentially it's the distribution of the first 16 water molecules. So in dark blue is the first water molecule, the closest one to cesium plus, the second, the third, and so on. And so this implies that molecule number 9 is essentially in between the two solvation shells. Then what I can do, I can look at the position of the maximum and the width of this distribution, and I plot here these two things, the position of the maximum and the width. And then I can calculate the XF spectrum. Oops. And you need to focus on the solid red line. And you can see in open symbols are the experiments by John Fulton, and these are the calculations using the point charge model. There are oscillations, but the amplitude is overemphasized, and the position is also not very good. Now I go to the polarizable model, and you can see visually a difference. These things become much flatter. This peak goes down at a different position, but I get, a slightly better description of the high K XFs. I put back the 2-body, and you can see now this peak grows, and here you have a better description of the first and second solvation shell, and definitely you're getting closer to experiment. You put the 3-body, and you are getting closer, and these things are changing as well. And then I put quantum effects, and these peaks are also changing. So now we don't have a model that is only better visually, but it's actually more physical because actually reproduce the hydration shell correctly when compared to the experiment. Okay, and so the conclusion is that now this model is able to reproduce these things very closely. And so the question is like, okay, now what can we do with these many-body models? We can do a lot of things. We have a paper in press in PNAS where we show how ice nucleates in the atmosphere. This is very important. People were talking a few days ago about climate and how clouds form. And ice is an important contribution because essentially understanding how ice form is going to tell us how precipitation may work. We had a paper last year in PNS when we understood the mechanism of ice nucleation. This is very important. If you live in Chicago and you want to fly out in winter, you spend a lot of time on the runway because the plane has to defreeze. And so now is what happens because you have materials that may prevent ice formation. And so we are now working with Peter, that was here a few days ago, and trying to use his pool method to try to design proteins that can, or peptide, that can prevent ice formation. Just today, we have a paper out in Nature Communication when we look at water in metal-organic frameworks. Metal-organic frameworks are porous materials that are very good at absorbing gas molecules. And so now we are working with Sean Gao at UCSD, trying to use machine learning now to design materials that can be used with our data-driven model to capture water from air that can work as a sponge in arid areas. And of course, now we can work with any molecular fluid. It's very easy to build these models because I just need 2-body, 3-body interactions and a good description of the classical polarization part, and I'm done. And so I can work with any mixture of CO2, water, hydrocarbon that are small. Okay. More interesting, I think, is this part. Because this is Marivi Fernandez Serra at Stony Brook that is using MBPol, so our many-body model, to develop a functional that works for water. So essentially, I think we are closing the loop. We started with the force field. We went ab initio. We went to a couple of clusters. We developed a data-driven model that now is informing density functional to get a model that actually works for water. So now what is the problem? The problem is that we don't know how to build these training sets. This is an after-the-fact analysis that we did with Michele Ceriotti, Gabor Schaning, and Jörg Beller to understand how our training set was looking for the water dimer. And so here are the distances. So this map is a sketch map by Michele. These are the distances between the oxygen atoms. You can see there is a lot of points where we are in the minimum energy region of the interactions here. If you look at the density, obviously I have a lot of density. The energies is very attractive in this region, more repulsive up here. And then if I look at the errors that I have with the permutation invariant polynomials, neural network, and gap, you can see they are more or less the same. Gap is definitely doing much better here. Yes, this is the error. Much better here, but we showed that in the training set, gap was overfitting. Interesting, if you go to the Twobody, actually now it seems that gap is having problems in representing regions where both the permutation invariant polynomials and neural network actually work very nicely here with the small errors. It's doing much better in this region where instead these two methods work very similarly. So now the question is how we can build this training set before doing the simulation. And so we have developed a very simple active learning approach, and we are using Matthias' Manybody tensor representation to learn two-body and three-body interaction that are distinct enough that can make our model able to represent the phase diagram under reasonable temperature and pressure conditions. And so just for fun, what we did was we took the cesium plus training set, and using this active learning, we were able to show that actually we didn't need all these 13,000 two-body interactions because we can learn these energies with a fraction of the training set. And it actually is working because if I do then the same simulations with a fraction of the configurations, here is, for example, 4,000 two-body configuration and 5,000 three-body configuration, where the full training set is 13,000 two-body and 30,000 three-body, you can see they're essentially indistinguishable between the two sets. And so obviously developing these more intelligent ways to define a training set will be a good advantage for us. And so here is the conclusion. So we are trying to now use machine learning in a different realm, trying to design materials that can be used in our data-driven molecular simulations. Hopefully people can benefit from this Manybody decomposition. We have this C++ library that is completely standalone that allows to do these Manybody simulations. At the moment contains only water, but we are going to put all the other things that we have been doing. And I just want to conclude with this. And so obviously we have a model, and the model has a well-defined realm of existence. And so here we see a gondola, and we can define a model that builds this gondola. But we need to also understand what is the environment, because we may think to be in Venice, but instead we are in Las Vegas. And so the validation and verification is always very important, because otherwise our prediction can be completely misleading. And so here are a few papers, and thank you for your attention.